All right, let's go through our Unit 7 free response. So here we go. We've got this situation where we've got random samples of 30 from each of these groups, so that's meeting our conditions as far as large enough goes. So we want to do multiple t-tests, and so the first question is, how many t-tests is this manager going to have to do? Because we got A, I guess are those types of customers, or each group. Okay, they categorize them in one of three groups based on their banking habits. Okay, so in order to do multiple two-sample t-tests, we're going to have to compare A to B, and then A to C. Okay, and then we'll have to come and compare B to C. And so that's how we'll have to do multiple two-sample t-tests. Because for means, we do not have a way to compare multiple means. Now in Unit 8, we do chi-squared, which is for multiple proportions, but we don't have multiple means. So there you go. You did not actually have to say 3, but you did have to list out all of those 3 different pairs that you would be comparing. Okay. Next asks us, basically this whole information goes through defining what a type 1 error is, okay? And so what they're doing is saying type 1 error is if the null is true, but we get a statistically significant result that causes us to reject the null even though it shouldn't be rejected. Okay, so that's what all of this reading here is. And they want to minimize or investigate the probabilities of those type 1 errors. So therefore, the first question is, if the probability of getting a statistically significant result, so you're going to get something that's going to lead you to reject the null, if the alpha is 0.05, and remember we've talked about how alpha is the probability of a type 1 error, because whatever the size of alpha is, that would lead you to reject the null hypothesis, when if in fact the null is true, you shouldn't. Okay, so they say the probability of getting a statistically significant result in doing a type 1 error is 0.05. What's the probability of not causing a type 1 error? Well, that would just be the rest of it. So, if this top 5% is the rejection region that would lead you to an error, then this bottom 95% is the part that would not lead you to the incorrect conclusion. So that's your answer. That's how you get credit for Part A. Part 1 of this in Part B. Okay, but now they say they're actually, we've got multiple tests going on here because we have those things. So they want to say, what is the probability that, right here, they call this a family error rate, and that's where at least one of the t-tests conducted was a statistically significant result. So that means we want to see which, in order to have at least one of them be a statistically significant result, then that means you have where both of them are. The first is, the second is not, the first is not, and the second one is. So you have these 3 situations which are happening when at least one of them is statistically significant. So you remember the probability of at least one is 1 minus the probability that neither one of them were statistically significant. So your computing options for this would be to either add up these 3 down here, where one or both are significant, or just do this 1 minus both of them not being statistically significant. So that's what they're showing here. So you can do 1 minus the probability of none, or, add up the 3 significant pieces. Okay? So either way, it's like that. Now, they don't like this being this high, so they want this in itself to be 5% or lower. So that's what part C is going to investigate. Okay? So that's just the scoring on how you got those components. So they say, what would we have to do so that it is conducted at an alpha of 0.05? Oh, hold on, we're not quite there yet where I was saying. But, so we have this situation where we have 1 minus the probability of none of all 3 of them. We want no significant results for all 3 of them. So that's 1 minus the probability that all 3 of them are not statistically significant. So 1 minus the probability that none of them are significant. None significant, all good. Okay? All right, so there's that. And you had to show your work on there. Now, I had a little issue with this last one because the way I wanted to solve it ended up not being an okay mathematical way to solve it. So let's take a look at what I did, because maybe you kind of would have thought this way as well. So they say we want that family error rate to be closer to 0.05. That's where we're saying here. See, 0.05. In that case, it's 0.14. Okay, so that's pretty high. They don't like that. So what do we need alpha to be so that when we do 1 minus the probability of none of them, it's close to 0.05 instead of that 0.14. Okay, so there's a few approaches. One of them, they just took alpha and they divided it by 3, and then they estimated it with that, and it got you pretty darn close to 0.05. So in fact here, we were really close. So you might could fiddle with it that way. The way I was thinking of it was, my gut reaction was to set it up this way. 1 minus the probability of none cubed is 0.05. So that was the way that I thought about it. Okay, instead of being 0.14, we went and set it at 0.05, set it where your boundary is. But then I took it to here, which wasn't correct mathematically. So what I did was I algebraically solved for P of n. And so then I subtracted 1, and then, see, therein lies the problem. Okay, because I guess it's saying the probability of getting a not statistically significant result. What's wrong with saying that's 1.05? That's saying that's a 105% chance of something. So it took me a little while, like when I realized it didn't work out correctly, what's wrong with it? Well, you can't have a 105% chance of something, and you certainly can't have multiplying 3 probabilities together and get something bigger than 100%. Okay, so therein lies the problem with my algebraic method of solving. What they did here was they got that 3 not statistically significant ones as 1 minus the significant ones cubed. That's then where they were able to go and do the calculating. Okay, because then this was the key. 1 minus the probability of none cubed, that cumulative result. All right, so I'm going to leave it right there and let you think algebraically about that. After seeing that problem, I kind of preferred this top method better because that really kind of threw me for a loop thinking about that bottom one. But after I saw it in play, then I understand why my answer, just going through the brute force of the math, didn't make sense. Okay, so there is how you had to do that, and of course showing all your work. You know, more than just a single test to be less than 0.05. So see, I would have probably gotten this. If I had done it my way, I would have just then gotten some wrong partial credit because of the algebraic components that I was wrong with. Okay, next. So this is 31 emperor penguins. They do a stem and leaf plot, and then they ask you to, they tell you the sample mean and the sample standard deviation, construct and interpret. So do a full panic, a 95% confidence interval. Okay, so construct and interpret. Do a full panic. All right, and again, in this incomplete grading guidelines, they just jumped to the conclusion. We are 95% confident that the average swimming speed of all emperor penguins is between 9.425 and 10.17. Okay, so that's that. I disagree with this scoring rubric because they say you had to have three components: context, conclusion, making sure it's about the population of all emperor penguins, and that you say it's 95% confident. So many things missing there. Okay, but I'm not going to go into that except for to tell you that this is unusual, that these are the only things that they would look for. So panic it, not just do all they included. Now, then a very simple experimental design question is, can we estimate this and generalize to all types of penguins? So I hope you realize that, of course, you cannot generalize to all types of penguins because this sample is only the emperor penguins, which I'm sure are very different than a bunch of other kinds of penguins. Okay, I'm not an expert, but I think that seems obvious that there's a lot of different kinds that aren't going to be going the same speed. So, and that's all they asked for that it cannot be generalized, and say that it's because this is only one type of penguin. All right, so there's the conclusion of your free response key for Unit 7.